Hello. This is a video about doing multiple linear regression in R and looking at the f-test and the ANOVA function and interpreting regression coefficients. So we're going to be looking at what's called the Ames Housing Data. This is a data set compiled from public sources by a statistics professor in Missouri. If you want to see more about where the data came from, there's an article here. Actually, there's a document here that says defines what the columns mean. For our purposes, it's the easiest way to get the data is to install an R package called model data. So once you install this, you won't have to do it a second time. So this just takes a minute. So I'm going to go ahead and comment out this line to remind myself that I don't need to install it again. Okay, the data set within this model data package is called Ames. So to load in the data set, I run this line. And this gets loaded. Actually, let's take a look. If we look at the class of this data, this is a TBLDF class, which is, I think, commonly called a tibble. This is one of these tidy objects. I'm more comfortable working with the raw R version of the data frame. So I'm going to convert that to a data frame. Okay, so this is a regular old data frame. We can do like head, Ames to take a look at the variables. There's a whole bunch of variables in this data set. So maybe a simpler way to just look at what variables are there. We can look at the call names of Ames, and then I'm going to pass that to sort to alphabetize them. So look, if you look here, there are 74 variables. Alley, bedrooms, above ground, building type, so on and so forth. The response that we're going to look at is called sale price. So this is the sale price in dollars. But we're also going to look at things like how big is the basement, how many square feet of is the house above ground, things like that. Now, if you start to run regressions on this data set, you'll see that there's a few outliers in the data with regards to the sale price. And so the person who compiled the data set recommends that you remove the outliers because these are sort of non-traditional sales. So the way I'm going to do that is I'm going to subset the data to only cases where the sale condition is normal. And I'm also going to just look at one-family houses as opposed to multiple family houses or condos or things like that. So this will control for a lot of things. And it also removes some of these outliers. So I'm going to use the subset function in R. The first argument is the data frame that you want to subset. And then the second argument are the conditions for subsetting. So what happens here is here's one expression here. Sale condition equals normal. This is our syntax for what it's going to do is it's going to look at this vector sale condition, and it's going to compare, that's what this double equal sign does, each element of sale condition to the string normal. And if the element is the string normal, then it's going to return a true, and if not, it's going to return a false. So this is going to be a big long vector of trues and false. And there's a true every time it's normal, and it's a false otherwise. What this line does is it does the same thing, but it compares the variable building type to one family, returns a true if it's a one family, and false otherwise. Now, between these two things, we have the AND operator. What this does is it looks at each element of this vector and each element of this vector And if they're both true, it returns a true. But if at least one of them is false, it returns a false. So this thing together is sort of one expression. And it's going to be a big, long true-false vector. And the way the subset function works is it subsets this data frame corresponding to the rows for which this vector is true. Okay, so we'll run that. So this will restrict our data set to cases where the sale condition is normal and the building type is one family. So actually, let's take a look at that. So if we do Ames dollar sale condition, this is going to be always normal. And if you look down here, this is a factor. Originally, it had several different levels: abnormal, adjacent land, yada, yada, yada. By the way, the couple of outliers were the cases where the sale condition was partial. Okay. Now, one quick note before we move on. What I've done here is I've taken this, I loaded in this data set Ames, and then I've put it as the input to this subset function, and I've reassigned that data frame to a variable with the same name, Ames. Now, generally, this is not a good idea because if you were to repeat the command, you could further alter the data frame in a way that you don't expect. But this one is actually safe because if I, let me show you, let's go through the whole thing. So if I do this and I type dim Ames, this has 2,930 rows. Now if I run this subset command, now I've subset it to 2002 rows. So I've taken a subset of the data. And if I were to run it again, the danger is that I would further subset in a way that I don't expect. But this particular subsetting will have no further effect because the sale condition of the subsetted data set is always normal, and the building type of the subsetted data set is always one family. And so this thing is going to be true. And so there will be no further subsetting. So if I run that again, suppose I do that by accident, I actually won't change the data set at all. So as a general rule, try to avoid renaming variables with the same name because it can do things that sometimes that you don't expect. But this particular instance is okay. It's safe. All right, so we're going to be looking at this data set, and I'm going to make some plots for you, but before I do that, I'm going to create a couple of new variables. One of the variables is year sold, so this is like 2006, 2007, 2008. One of the plots I'm going to make is sort of the sales across time, and so I want a more granular time axis. One of the other variables is month sold, 1 through 12. So I'm calling Ames year frac for fractional year as the year plus the month over 12. And then another variable we're going to pay particular attention to is the number of square feet of finished area in the basement. By the way, if you're unfamiliar with that term, many basements, which is the area underground, are unfinished, meaning that it just looks like concrete floors and pipes everywhere and all that. But some people choose to what's called finish your basement, which is to make it look nice, make it look like an above ground floor by putting in carpet or flooring and putting up drywall on the walls and giving it a nice ceiling. So there's no single variable for the finished square feet of basement. So I'm going to define it as the total basement square feet minus the unfinished basement square feet. There are a couple other variables that you could use to define this, but this I thought was a simple one. Okay, so that's finished square feet. This is fractional year. And let's just go through and do some exploration of the data set. So I'm going to make a bunch of plots. For every plot, I'm going to put sale price on the vertical axis, and then I'm going to look at a bunch of different choices for the horizontal axis. So the first one is the year fractional. So just to see how things operate over time. So there's maybe some interesting thing here. One of the interesting patterns is that it seems that there are fewer sales around month 0 and month 1. So like December, month. So 2007 would be 2006 plus the 12th month over 12. So this is actually December 2006, and this is January. The first one is January 2007. So there are fewer sales in winter. There are more sales in the summer. It looks like the prices are higher in the summer, which might actually be true, but this could also be an artifact of just the fact that there are fewer sales in the winter. It doesn't look like home prices have really changed a lot over time. But of course, to understand that, you would have to sort of control for whether different sizes and types of houses were being sold over different periods. There was in the U.S. a housing crisis in 2008. It doesn't look like there's really strong evidence that the prices dropped, but maybe a little bit. That's something that might be worth investigating in this data set. Okay, that's year frac. One of the important variables is above ground living area. So this ranges from like 500 square feet, which would be a small house, to over 3,000 square feet, which is a very big house. And the sale price is very predictable based on the size of the house in square feet. So this is going to be an important area variable. Number of bedrooms above ground. Looks like, when there's lots of bedrooms, it's going to tend to be a more expensive house on average. Number of full bathrooms. Full bathroom, I think, is defined as a bathroom that contains either a bath or a shower. Half bathroom is a bathroom that does not contain a bath or a shower. Let's see. By the way, there are better ways to plot these sort of discrete variables. We'll take a look at that in a later lecture. Here's total rooms above ground. Looks like the prices increase with that. Basement square feet. Looks like prices increase as you increase the size of the basement. But by the way, of course, if you want to sort of understand the effect of basement square feet, you'll probably want to control for the total number of square feet, or the above ground number of square feet. Let's see, this is unfinished basement square feet. All right, so this is just doing some exploratory analysis of the data. By the way, if you want to make the code a little bit more readable, you might find that this sort of Ames dollar syntax is not very readable. You could write a function that takes in just the name of the two variables and plots them. So here's an example of such a function. You'll be looking at in your labs how to create your own custom functions. So this is just a pretty simple one. This is a function with two arguments, which are the two variable names, and then I'm making a plot with the first variable name and the second variable name. By the way, if you have a data frame and you want to access one of the columns, there's various ways to do it. One way is with this syntax here, this $ syntax. Another way is to use the square brackets. So you could do Ames square bracket, all rows and column sale price. So that will access the sale price variable. A third way to do it is to remember that a data frame is actually a list. And to access elements of a list, you can use the double square bracket syntax. So what this does is this accesses the column named var1. This is a bit of a digression, but this is a little bit safer. So for example, if you do Ames dollar, let's check this in real time. I hadn't planned to do this, but so if I do Ames dollar sale and I do enter, I get null. If I do Ames dollar sale PR, okay, it does something weird. There's no column named Ames dollar sale PR, but R tries to complete your sentence, and it checks to see if this is a partial match for one of the variable names. So this one is a partial match for 3 variable names. So if you do this, it returns null. But if you do this, it's a match for only 1 variable name. So R tries to guess that you want to see the sale price one, and it will return it for you. Now, if you were to try that with this syntax, sale PR, it returns null. So this is sort of a personal choice, but when possible, I like to use this double square bracket syntax to access columns of a data frame. The reason for that is because I've run into errors before where I thought I had defined a variable and it wasn't defined the way it was supposed to, but it was a partial match for a different variable, and that caused all sorts of problems for me. So if you want to avoid this partial matching, you can use this double square bracket syntax. Okay, so that was a long story to tell you how I define this function, and you'll be getting some more practice defining your own custom functions. So this, if I call this plot Ames function, which I defined, maybe you think this looks a little bit nicer. Maybe you prefer this one. So this could be personal preference here. Got to define it first. And then I can run all these. It makes all the same plots. Okay. So if you want kind of a exercise to practice with functions, one thing you could try is this plot kind of stinks because since I'm passing var1 as an argument to the function, the function doesn't know what the variable is actually named. But you can modify this function so that it puts the correct variable name on the axis. So if you want to exercise to practice in R, try improving this plot Ames function to include informative axis labels. All right, so before we start looking at a bunch of different models, I'm going to start with a really simple one, and this is going to be instructive for how we interpret the regression coefficients. So I'm doing these on one line just to make things a little bit more compact. But if you look at the line, we're calling the LM function, and the response is sale price in dollars. And then I'm going to regress that on 2 different variables: basement unfinished square feet and basement finished square feet. And then, of course, I have to tell the LM function which data set to look at. Then I'm going to take this whole thing and I'm going to pass it into the summary function. So I'm doing summary of LM of a particular model. So let's run that line and let's look at the output. Okay, here's the output. There's an intercept of $58,654. So one way you could think of this is the expected price of a house with no basement. So that averages over a whole lot of things. So maybe this isn't particularly informative. Now, if you have a house and you increase the number of unfinished square feet while holding the number of finished square feet constant, you increase the sale price by $108 per additional square foot. So you can think of this as like you have a house with a basement and you find a way to increase the size of the basement, but you increase only the unfinished portion of the basement, and you keep the number of square feet of the finished portion constant. Now, to reverse that, you can think about this coefficient, which is increasing the amount of finished square foot of basement while holding the number of unfinished square feet constant. So you think of this as you have an existing basement, it has some number of unfinished square feet, some number of finished square feet, and you find a way to add square feet to the finished portion without changing the square footage of the unfinished portion. And this is more lucrative. So people prefer to have a finished basement, and so you increase the sale price of the house by more. So about $126 per square foot. By the way, so that's the interpretation of these coefficients. By the way, the residual standard error is 55,190. So this means you can expect this model to predict the sale price within about $100,000 or so, which is not actually not really a very good model. Okay, so let's alter this model a little bit. You might think that this model actually isn't all that interpretable because when people are thinking about making modifications to their house, they're not generally going to change the overall size of the basement because that's very hard to do. One thing people do in practice is they take an unfinished basement and they convert it to a finished basement, or convert some portion of the unfinished basement to a finished basement. And that's not what these coefficients measure. These coefficients don't measure the impact of converting unfinished to finished. It's like adding additional basement square footage on top of what's already there. So that's what the interpretation is. I don't mean to say it's not interpretable, but it's maybe not as relevant for someone who has a house and is thinking about converting unfinished space to finished space. So this next model, the two variables are unfinished square feet and total basement square feet. And then we're going to think about, actually, let me make a change on the fly. I'm going to change this to finished. So the two variables are basement finished square footage and total basement square footage. Okay, and here's the output. So we're going to have to think carefully about how to interpret these coefficients. But again, if you get stuck, just repeat this mantra in your head that the interpretation of the regression coefficient, it's the effect of changing that variable while holding all other variables constant. So let's apply that in this case. So this coefficient means this is the effect of increasing the amount of square footage of finished basement while holding the total constant. So if you think about what that means is you have a fixed total basement size and you're increasing the number of finished square footage of that total size. So that's really what that means is you're taking unfinished square footage and you're converting it to finished. So you're increasing the number of finished square footage without changing the overall total. So that's exactly how you interpret this coefficient. So that means if you take 1 square foot of unfinished basement and convert it to finished, you can expect to increase the size or the price of your house by $17.63. Okay, now let's interpret this coefficient. What this means is if you increase the total size of the basement by 1 square foot while holding the finished portion constant, you increase the sale price by $108. So what does that mean? If you increase the total size by 1 square foot while holding the finished portion constant, that means you're adding an additional square foot of unfinished space. And if you'll notice, this coefficient is exactly the same as this coefficient from the previous model. And that's the way it should be, because these have the same exact interpretation. By the way, we haven't changed the actual models at all. We've just changed how we interpret the coefficients. One way of noticing that is the residual standard error is 55,190 here, and it's exactly the same here. Okay, so that's two different ways to express the same model. Just for fun, let's see what happens when we put all three of these variables in the model. So we're going to put unfinished square foot, we're going to put finished square foot, and total square foot in the model. And before we do it, actually, let's just go for it. Okay, and here's the output. You'll notice that for the last variable, it puts an NA here. So let's think about why R did that. And let's think about why it does that in the context of what this coefficient means. So what this coefficient would mean, if we were actually able to include it in the model, is we're increasing the total basement size while holding the unfinished size and the finished size constant. Now, because the total basement size is equal to the sum of these two things, it's this plus this, it's impossible to increase the total basement size while holding these constant. And R correctly tells us this model doesn't make any sense, or this coefficient doesn't make any sense when you control for these two things. So basically R is saying we have no information. So R doesn't know that the total basement square foot is equal to the sum of the unfinished and finished. That's like a concept that exists outside of the data set. But R does know that in this data set, there's no information about this quantity, about the effect of increasing the total basement size while holding these two constant. So R correctly says that there's actually no information about this coefficient in the data. So I'm going to return NAs for this and leave these as they are. So R does actually, when you get NAs here, this is actually completely sensible. This is what it really should do. All right, that was just a bit of a warm-up to get us thinking. Now let's go and fit some more complicated models. So in this first model, I'm going to add the above-ground living area, unfinished square foot of basement, finished square foot of basement. As before, we're not going to add total basement square foot because that's kind of redundant given these two. The number of full bathrooms, number of half bathrooms, the number of bedrooms above ground, and the total number of rooms above ground. And then we're going to tell it that the data set is Ames. So I could run this line, and that works. But just as a programming practice, doing something like this is kind of a bad idea because this kind of goes off the page. It's a good idea, just like with a newspaper where they organize it in columns, to keep the size of the columns that your text fills to be somewhat short. It makes it easier to read. So this is the exact same model with what, in my opinion, is better formatting. So there's still going to be two arguments. This is the model formula. This is the first argument. And and this data is the second argument. But these are put on separate lines because the line gets to be too long. And then the first argument, which is the model formula, I'm going to actually format this a little bit nicer too. I'm going to put the sale price here, and I'm going to indent all of the covariates. And then on top of that, I'm going to try to organize the covariates in terms of type. So these are basement variables, these are bathroom variables, and these are number of rooms variable. So this is just a different way to format. There really you should try to follow some conventions when formatting, but you can deviate a little bit if it makes sense. So this is an example where, this is all one argument. So, but there's actually some meaning to what the first part of the argument is relative to the other. So I've further formatted this. So this makes it a little bit easier to read, and it's the exact same model. Okay, let's look at the output. All right, so the intercept is a negative number. Again, this is not going to be particularly interpretable because this is the price of a house where for example, the total above ground living area is 0. And all these other variables are 0 as well. So that's just like a piece of land. And this data set actually only contains sale prices for one-family houses. So it doesn't include any information about the size of the lot. So this wouldn't be a good model for predicting the sale price of a lot with no house on it. Okay, so let's go to the other variables. All right, what does this coefficient mean? This means increasing the above ground living area by 1 square foot while holding all these other variables constant. So if you look at the other variables, it's the size of the basement. So this is like increasing the upper living area while keeping the same size basement. So like sometimes people will put an addition on their house, for example, without increasing the number of bathrooms or the number of bedrooms or the total number of rooms. So this is like this is the effect of just like making your living room bigger or making your kitchen bigger. So you get $76 per square foot in this model. The effect of increasing the size of unfinished basement is smaller, 56, and the effect of increasing the size of the finished basement is $83. Again, while holding everything else constant. You're not increasing the above ground living area, for example. Okay, now let's look at these variables. And this might tell us something about sort of preferences of home buyers. If you increase the number of full bathrooms by 1, while holding every other variable constant, you increase the sale price by $21,000. If you increase the half baths by 1 while holding everything else constant, it's only $16,000. So what does that mean? A bathtub or a shower is worth about $5,000 additional dollars. Now this one is going to be interesting. If you increase the number of above ground bedrooms by 1 while holding everything else constant, you actually decrease the sale price of the house by $18,000. So this may come as a surprise to you. And just an anecdote, I was working with a researcher, and he brought me a housing price data set, a different housing price data set, and got exactly the same result. So I think this is actually not sort of an anomaly. This is actually a real effect of housing prices in today's age. And I think this negative coefficient makes sense. So what I want you to do is to pause the video and think about why this negative number makes sense. And remember the interpretation of the regression coefficient is the effect of this of increasing this variable by 1 while holding all other variables constant. So go ahead and pause the video and think about that for 30 or 60 seconds. All right, here's my interpretation. Since this is the effect of increasing the number of bedrooms by 1 while holding everything else constant, this includes the total above ground living area. So this is like, for example, if you had a big bedroom and you chopped it up into 2 little bedrooms, you would increase the number of above ground bedrooms by 1 while holding everything else constant. Actually, that's not true. Because you're accounting for total rooms, you would actually increase the total number of rooms. But this coefficient is smaller, so you would still decrease the sale price of the house by about $15,000. Actually, a better example is if you had like a room upstairs, which was classified as an office, and you converted that to a bedroom, then you would decrease the sale price by $18,000. It's not, so one thing you might think about is, well, you increase the number of bedrooms. It's like you're adding an additional bedroom, so that should increase the sale price of the house. But that's not actually what this means, because you're controlling for the overall living area. You're not actually adding additional space to the house with this coefficient. You're converting existing space to a bedroom. So I think this makes sense. If you have a house that's all bedrooms, it's probably not going to be a very desirable house. This may make a lot of sense in terms of the the number of people living in U.S. families has been decreasing over time. So there's probably been some attempts in housing to convert what were bedrooms to not bedrooms to make the house price more desirable. Okay, if you increase the total number of rooms, it does go up by a little bit, but this effect is smaller than increasing the number of bedrooms. All right, a couple other things to look at. The residual standard error is about $33,000. So you can expect this model to predict the sale price of a house by, within plus or minus 2 times $33,000, so plus or minus $60,000, which is a better model than the basement model. You'll notice that all of these coefficients are significant at the 0.01 significance level. Some of them are even much more evidence that they're not zero. This is probably largely a function of the fact that there's 2,000 observations in this data set. So if there's any effect, this data set is going to be able to find them. R squared is about 0.8, which you may think is good or bad, depending on your preferences. And then there's an F statistic here. By the way, the reduced model for this F statistic is the model that has only an intercept in it. So by default, this R, when you do summary of a model fit, R will by default print out an F test to compare the model that you selected to a model with only an intercept in it. And it does the F test for you. It gives the numerator degrees of freedom. This is the F statistic. This is the numerator degrees of freedom, and this is the denominator degrees of freedom, which is the same as the residual degrees of freedom for the full model. All right, so the next thing we're going to do is we're going to look at the same model, but we're going to look at houses from one particular neighborhood. And so there's an Ames neighborhood variable, which lists a bunch of neighborhoods in Ames, Iowa. I've been to Ames, Iowa, but I'm not particularly familiar with the neighborhoods. So I just picked one of them that sounded fun. Okay, reason we're going to do this is because when you do F tests on this data set, this model for this data set, It's not particularly interesting because everything is like wildly significant. So we're going to look at a smaller data set so we can get some more interesting results for f-tests. All right, so this is the Old Town data set. Let's look at just the size. This has 76 columns and 177 rows. So there are 177 sale prices in this data set. All right, so this is going to be the exact same model we fit before, but fit to the Old Town data set. So let's do this. Look at the output. You see that there are fewer things that are statistically significant. Again, I think this is largely because this is just a smaller data set. The more data you have, the more likely it is that you're going to have evidence to see effects in the model. So a lot of the coefficients are very similar. In this case, one additional above ground living area, $75. The effect of increasing the number of bedrooms is negative as before. And here, now the sign of the increasing the number of above ground rooms by 1 while holding everything else constant is also negative. And here the effect of a full bath is actually smaller than the effect of a half bath. But there's uncertainty about these coefficients. Maybe this seems like this doesn't really make sense. A full bath really should be worth more than a half bath. But there's a lot of uncertainty about these. So maybe we can't conclude that this effect really is bigger than this one. Let's see. By the way, we could do a t-test for that, but that's a little bit more to test whether this coefficient minus this one is equal to 0. But that's a little bit more evolved. We could do that in a later lecture. All right. The reason it's a little bit more involved is because it involves a difference of coefficients, which means you have to figure out what is the standard error for the estimator of this difference, which involves not only the standard errors of the individual coefficients, but the correlation between those two coefficients. Okay, so this is we're going to take as our full model, and we're going to look at a couple of different reduced models and do the f-tests for them. Okay, so the first reduced model we're going to look at is a model that does not include bathrooms. So you might say, I want to test the hypothesis that the number of bathrooms provides no additional information about the sale price after you control for above ground living area, the basement size, number of bedrooms, and the total number of rooms. So to test that hypothesis, you can't just do a t-test, because this involves the hypothesis that this coefficient is 0 and this coefficient is 0. So we need an f-test for that. So the way this works is we set up our reduced model. We fit the reduced model. We don't need this for now, but this is the summary for that model. So it does not include the bathrooms. And then we have to collect 4 quantities from these two models. So the residual sum of squares from the reduced model, you just do reduced model, M21, I'm calling it, dollar residuals, and then you square it, and then you sum them up. The residual degrees of freedom is in a field called df.residual. So that's residual degrees of freedom from the reduced model. The residual sum of squares from the full model is M2. The full model is M2, dollar residual squares, and then pass that through sum. And then these are the full model residual degrees of freedom. And then it's pretty simple from here on in. We just use our formula for the F statistic. This is the numerator, and this is the denominator. And then the p-value we can get from the pf function. So the first argument is the statistic. The second argument is the numerator degrees of freedom, which is df0 minus df1. And the second argument is the denominator degrees of freedom, which is df1. By the way, this might seem slightly confusing because in the function, they refer to the denominator or the numerator degrees of freedom as df1. That's the argument. And in my code, I'm referring to the denominator degrees of freedom as df1. So make sure you keep that straight. So that's the p-value. The pf returns the area under the curve that's smaller than f. We want the area under the curve that's bigger than f because large f statistics constitute evidence against the null model or against the reduced model. So this is the p-value. And that number is pretty small, 0.008. So this means that we have reasonably strong evidence that the effect of bathrooms is not 0. By the way, if you have trouble keeping track whether you should do 1 minus or not do 1 minus, there's another argument to the df function called lower.tail. So by default, this argument is set to true, which means it does the lower tail probability, which is the probability less than some number. If you set lower tail equal to false, it will do the upper tail. So it'll do the probability bigger than the first argument. And so this gives the same number as 1 minus pf without the lower tail set to false. Okay, so that's our p-value, and we can check our work against the ANOVA function. So the way the ANOVA function, well, let me step back. The way I like to use the ANOVA function is to use it with 2 arguments that contains 2 different models. So what this will do is it will treat the first argument as the reduced model, and it will treat the second argument as the full model. So you can put in, so let me just show you real quick. If I go over here, if I do ANOVA M2, so if I just give it 1 argument, the full model, it tries to figure out what f-test you actually want to do, and it does a whole sequence of f-tests. And none of these are the f-tests that we actually want. So to keep things straight, I like to just fit exactly the reduced model that I want to do, and then I give the ANOVA command 2 arguments, and then I'm sure exactly what it's doing. It's doing the f-test to compare the first argument as the reduced model and the second argument as the full model. Okay, and here you can see that it spits out some information. It spits out the 2 residual sum of squares, the difference in degrees of freedom, which is 2 in this case, because we set 2 coefficients to 0. This is the difference in sum of squares. This is the actual f statistic. So if we didn't print that out, but f is 4.9463, which is the same as this. And then this is the p-value that we got, 0.008. Okay, so we did it right. We did the calculation for the f statistic right because it agrees with what R gave in the ANOVA function. Okay, so the last thing we'll do is we'll do another f-test where we keep the bathroom information, but we take out the basement information. So this is our second reduced model that I'm calling M22. This is designed to test the hypothesis that the unfinished basement coefficient is 0 and the finished basement coefficient is 0. So that's the reduced model. If you like, there's the summary. See, it doesn't contain the basement variables. And then I'm not going to do all the calculations for the f statistic by hand. I'm just going to go straight for the ANOVA function. Remember, the first argument is the reduced model, M22, and the second argument is the full model. Okay, so this says that the difference in degrees of freedom is 2. The difference in the sum of squares is this number. And the f statistic is 1.3659. So this f statistic is smaller than the one we got for the comparison against the model that has no bathrooms. And the p-value is larger, which means we do not have strong evidence from this data set that the basement variables, that their coefficients are not 0. Okay. So if you were to do the same thing for the full data set, you would get a significant p-value, probably highly significant. But if you were to look at a smaller data set, you do not. And this is really largely a function of the smaller data set contains less information about the effects of all these different variables. And the p-value reflects that. So remember, the p-value is a measure of the strength of evidence against a null hypothesis.